Every day, millions of tons of steel, concrete, and asphalt hang suspended in mid-air, supporting heavy, unpredictable traffic. To our eyes, a bridge like this is perfectly still, but physically, it is engaged in a constant, invisible tug-of-war against gravity. To keep that structure standing, physicists rely on strict conditions of balance. An object is in equilibrium as long as its acceleration remains zero. Look at the schematic. A car cruising down a highway at a constant velocity maintains the same state of equilibrium as a parked car. Both systems are balanced because their motion is not changing. This gives us the first condition of equilibrium. If you add up all the horizontal push and pull forces, they must cancel out to zero. The same is true for the vertical forces. Mathematically, the sum of forces in the x direction and the y direction equals zero. However, balancing linear forces is only one part of the equation. Imagine two hands gripping a steering wheel. The left hand pulls down with 50 newtons of force, and the right hand pushes up with 50 newtons. The net vertical force is zero, yet the wheel still spins. In physics, we call this a couple. If a bridge or a skyscraper experiences that same twisting effect from the wind, zero net force won't prevent a collapse. Achieving stability requires us to account for the forces trying to rotate the object. This brings us to torque. While linear force dictates how an object moves in a straight line, torque is the physical quantity that dictates how an object rotates around a specific axis. Look at this breakdown of a wrench turning a bolt. The torque equation is represented as tau equals force times r. The force you apply is important, but the distance from that pivot point to where you apply the force, the moment arm, or r, is equally critical. A common mistake in calculating torque occurs when the force is applied at an angle. If you pull on that wrench at a 45-degree angle, only the perpendicular component of your force, calculated as F sine theta, actually contributes to turning the bolt. The rest of the force just pulls against the pivot. To get maximum rotational impact with minimal physical effort, you must apply your force as far away from the axis of rotation as possible at a perfect 90-degree angle. This leads directly to the second condition of equilibrium. For an object to remain completely rotationally stable, the sum of all torques acting upon it must be exactly zero. This diagram demonstrates the principle of moments. The heavier weight sits closer to the fulcrum, generating a specific amount of torque in one direction. To achieve balance, the sum of all clockwise torques must perfectly equal the sum of all counterclockwise torques. When engineering complex systems, calculating all these forces gets tricky, but there is a mathematical strategy to simplify it. Any force multiplied by a distance of zero equals zero. By placing your calculated pivot point directly over an unknown upward force, like this left pillar, that unknown force drops out of your torque equation entirely. A structure reaches absolute equilibrium when both of these conditions are met. Linear push and pull forces must net zero, and rotational torques must perfectly balance. Center of mass and center of gravity are distinct physical properties that only align in a uniform gravitational field. On Earth, for a small object like a cube, they sit in the same spot. But for a massive structure like a theoretical space tether, the bottom half weighs more than the top because gravity is stronger near the surface. This causes the center of gravity to sit lower than the geometric center of mass. The location of that center of gravity dictates an object's stability. When a cone rests on its wide base, tipping it forces its center of gravity to rise, creating stable equilibrium. Balance the cone on its tip, and any slight nudge causes the center of gravity to fall. This is unstable equilibrium. Lay it on its side, and rolling it keeps the center of gravity at a constant height, resulting in neutral equilibrium. Engineers manipulate these three states constantly. By giving a race car an exceptionally wide wheelbase and placing the heaviest engine components as close to the asphalt as possible, they force the center of gravity downward to maximize stability. Mastering how forces interact, how torque creates rotation, and how mass distribution dictates stability forms the core baseline for all structural physics. The two conditions of equilibrium provide the mathematical toolkit required to calculate exactly how any structure resists the pull of gravity and stays standing.